We're going to see where we come up to on time for this one. This is either going to be the atom and periodicity and nomenclature, or some part of that with another video to go with it to cover 3 and 4. There's a good bit of information in here, but remember, everything's multiple choice. Everything's covered equally on the final. This is just the stuff that could be there. For your scientists, again, multiple choice. First thought of the atom, Democritus, Democratus, Democritus. Wrote the first atomic theory, Dalton. He had a law of partial pressures, too. Plum pudding model, Thomson, Thomson. Alpha particles in gold foil, Rutherford. Yes, he did that. He was the one that discovered the positive nucleus. Planetary model, Bohr, also called the Bohr model. And last but not least, our current mathematical quantum model is Schrodinger. I'm pretty sure that one's written on one of your other practices somewhere. 3 ways Dalton's atomic theory differs from what we now know. Number 1, he didn't think you could break down an atom, which meant he didn't believe in protons, neutrons, and electrons. We know those are true. He said atoms of one kind are always the same. So like every single nitrogen atom would always be the same. We know that they can lose and gain neutrons and electrons. So they're not all exactly the same. People will also say that Dalton was wrong about making atoms from other atoms. Atoms do break down into smaller atoms. Atoms are fused in colliders. So that's a matter of, do we call that a chemical reaction or is that some physics thing? But it is true that we're able to do that now. Your dual nature of light is wave-particle. So sometimes light can act like a wave, and sometimes it can act like a particle. We talked about how in class. Normally light's a wave. Like, light doing light things is a wave, but the photoelectric effect, where it knocked electrons off a metal, showed that it could be a particle, too. And speaking of particles, we've got our couple charts coming up here on subatomic particles and on counting protons, neutrons, and electrons in atoms. So, protons. Where are they? They're in the nucleus. Neutrons are also in the nucleus. And electrons are in orbitals, also known as they're not in the nucleus. So I think I got my whole word in my video, making sure. There we go. They are not in your nucleus. We've got, what else do we have here? Hold on. Just like always, everything just opened on my computer. There we go. Yeah, and you got my window in the background too. That's my window. So my charge here, you can see if you write the symbol, my charge on a proton is positive. My symbol is P+. My charge on the neutron, there is none. So I use an N with a degree sign. And for my electron, it's negative. So I use E negative. As far as mass goes, we're not going to do the kilograms mass. We're going to talk in terms of atomic mass units. Protons are 1 AMU, neutrons are 1, and electrons are so little we call them 0. When we're counting these in atoms, though, we need our periodic table. For atomic number and mass number. Atomic number is the number where I find these on the table. Arsenic is 33, and calcium 20, cesium 55, the phosphorus 15, and manganese 25. Your mass number is your mass rounded. So arsenic, 74.92 gives me 75. Calcium, it's 40.0 something, so it's just 40. Cesium, 132.91, so 133. Phosphorus, I know some of these, 30.974. And manganese, I think it's close to 55. Yep, close to 55. Great. Counting protons, neutrons, and electrons, we done with that. So, protons, there's no charge on this, so that means that protons and electrons are equal, and they equal the atomic number. You know what? Protons always equal the atomic number. That's the definition of atomic number. How many protons an atom has? So that's pretty cool. And anytime I don't have a little charge, like calcium does, phosphorus does, anytime I don't, then my atomic number and my protons equal my electrons, because that's what having no charge means. Cool. Neutrons is going to be mass number minus atomic number. Mass number minus atomic number, so this looks like 75 minus 33 looks like 42. I like 40 minus 20, that's 20. 133 minus 55, that's probably 78, but I'm going to check. 133 minus 55, yep, 78. 31 minus 15 is 16, and I like this one. 55 minus 25 is 30. I have 2 blanks left to fill, and they're my number of electrons in my charged atoms. So, let's see. It would be, if it's positive, my number of protons minus my positive charge. Because remember, electrons are negative, so that means a plus 2 means I've lost 2 electrons. Electrons are negative, so this means I've gained 3. The changed ones are calcium with 18 electrons instead of 20, and phosphorus with 18 electrons instead of 15. Remember, if you've gotten to a group 18 number, 2, 10, 18, for your number of electrons, you've done something right. 3 differences between orbits and orbitals. Orbits are flat, orbitals are 3D. Orbits are where electrons always are. Orbitals are where electrons are likely to be. Orbits can only be circular. Orbitals come in a number of shapes, the SPDF thing. And orbits aren't real. We currently support the theory that atoms have electrons in orbitals. Cool. Ground state is your low energy state of an electron, and excited state is a high energy state of electron. How does an atom move from the ground state to the excited state? It absorbs energy and bumps the electron up, so it's absorbing energy. And after the excited state gives off energy, the electron goes back to ground. So energy added bumps an electron to excited state. Energy released brings it back to ground. Defining my following principles, I'm more worried about what they say than their name. Aufbau principle is important. Electrons fill orbitals from low energy to highest. Electrons fill from lowest to highest. They're lazy. They do the low work first. Hund's rule says I partially fill each equal orbital before I completely fill any. So I partially fill, if I've got the 3 lines straight across, I got to put 1 electron in each before it goes in all of them. Pauli exclusion, we didn't really talk about it that way, but what it said is that basically, if 2 electrons are in the same orbital, first of all, 2's the most it can hold. 2's the most any orbital can hold, and that's important. And they have to have opposite spin. Spin can be plus 1/2 or minus 1/2. We're not going into huge detail and quantum numbers in this, and we're not going to do orbital diagrams. I'll put up the orbital diagram for boron, but it's not going to be a focus. So SPDF, each of them holds 2 electrons per orbital. That's your definition. Holding 2 electrons per orbital, that's all I've got. So can't do any more. Gotcha. Number of orbitals, S has 1, P3, D5, and F7. So multiplying each of those by 2 gives me my total number of electrons held. S has 2, and P has 6, and D has 10, and F has 14. That's how that always works. So I'm putting this chart up while I'm talking, and I'm only going to put up the very beginning because I don't feel like we're going to have enough room to do more on here, and I don't feel like we're going to have enough time either to go through huge examples. I've got a couple electron configurations to write, and then we'll catch those and hopefully the end configuration before I run out of time. Remember, S holds 2, P holds 6, D 10, and we're not really going to use F, but it's 14. If I'm drawing an orbital diagram, I'm showing these as lines. So if I were to write a configuration for boron, it's number 5. All I'm going to do is say that those 5 electrons fill in this order. So 1s can hold 2, 2s can hold 2, and 2p can hold 1. If I were drawing that I would do one line for each s orbital and an up and down arrow. I'd show p orbitals as 3 holding a single electron. That was more relevant when you were doing questions from memory, like writing them out from memory. I couldn't get this in a multiple choice in Google Classroom format, so this one kind of went. I do have you picking out correct configurations though. And we'll start with carbon with 6 electrons, which I'm starting with carbon with 6 electrons because it was just one more. It was just one more. Potassium is next, K, 19 electrons, and I'm going with the idea that you learned how to do these mostly in class and on your other review. So I'm going through them pretty quick. There's my first 10 electrons after 2p. 3s uses 12. 3p was 18, and 4s finished up 19. If you're stuck on this, go back to my other video and check that out for knowing how. 3p6 is my last full p orbital. So argon, 4s1. Ruthenium, I believe, is my next one with, oh boy, 44 electrons. So we'll start with what I got. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's the first 20, and we already knew that was the order. After 4s comes 3d on 3d10. I'm now at 30 electrons used. 4p6 takes me to 36. 5s2 to 38. And let's see. 1, 2, 3, 4, 5, 6 over 38 should be 5s, 4, d, 6, because that's 36, 38, 44. For my noble gas, 4p6, count down, helium, neon, argon, krypton, and write the rest, 5s2, 4d6. So for the ones where you're getting the N configuration, there's none that you have to do this on the test, but it could help you if you're checking them. 2s2 would be second row down, hydrogen, then lithium. 2s2 would be then count 2 over. Lithium, beryllium. Beryllium ends in 2s2. For p orbitals, go to the p block that starts with boron. The first row is 2. So boron is 2p, aluminum 3p, gallium 4p, and count over 3 including gallium. Gallium, germanium, arsenic. Arsenic ends in 4p3. 3d9. 3d is the top row of the D block. So I start with scandium and count over 9 to copper. Copper ends in 3d9. 3p6. I know that's a noble gas. Always a noble gas if it's p6. Neon would be 2p6, so argon is 3p6. 1s1's hydrogen. I'm done. It only has 1 electron. 5d3 is the third row down in the D block, and count over 3 to tantalum, 73. Do I have you doing these in the test again? No. Do you need to be able to do them well? No, but they can help you check your answer, even if you just realize that if it ends in S, it should be in the S block over to the left. If it ends in P, it should be in the P block. If it ends in D, in the middle. Nothing ending in F orbitals. Looks like this video is out of time. We'll do periodicity and nomenclature together in the next one, and that will be recorded very soon. See you then.